In this problem, we have the opportunity to look at the effects of combined loads on a beam or a shaft. If you look here at this problem, what we have is this T applied, which is an applied torque about the x-axis, essentially treating the structure as a shaft or a rod that's being twisted. When we look at this applied force P, that is a transverse load, we essentially have a beam that has a circular cross section coming out of the wall. We are going to look at this problem as a superposition of the effects from this force P and the effects of this applied torque T app. Now, another way to draw this type of system to kind of get to a quick illustration that's 2D in nature is what you see down here. So what Jeff Hansen and others would suggest is that you can go ahead and just draw the cross section where we have this point A in perspective, and we have this P, which actually ends up being the transverse force or internal shear force P across this cross section. And there's also going to be internal torque, that's Tap, as you see here. And we can go about and sketch the effective shear stresses that we're expecting just on this figure. I'm going to go into a little bit more detail that describes how to think about these loads step by step, and hopefully will make it clear how you might be able to quickly go to this diagram and quickly calculate out what the shear stress due to P is and what the shear stress due to T app might be. For the first time you see this, I think it's not a bad idea to go back and look at these structures as a beam and as a rod. So let's do that. Here is a beam that we have with load P being applied to it, and the location of interest is at A. And up here, we're going to draw a rod or a shaft with the applied torque being on the end closest to us. And there again is this location A of interest. Now, let's go ahead and focus on the beam aspects of this problem. And what better way than to draw a beam? So here is the beam. And now, which way is this beam facing, and what is its orientation relative to the x, y, and z coordinates that we have in the initial problem? So we're going to define that x is still going along the axis of the beam. So here's a longitudinal axis, and we're going to say that y is coming out. So look, y was coming out up the top through A. As the question says, that A is on the, or is at the most y positive line on the surface of this cylinder. Okay, so y is coming out up this way, and it's coming out at us, and that means that z, okay, is going to be going downward. All right, so essentially we've taken this structure and we've rotated. It's now facing us, such that load P will be going in the minus z direction and be going upward. A is at this location, which is on the neutral axis, you could say, so across, because it's on the outer surface, right? So if you want to use the Hibbler terminology, the longitudinal axis would be right along the middle. Okay, so it's actually not drawn in either of these figures or in any of these three figures. But I could say that I've drawn now this longitudinal axis here, or I've also drawn a potential neutral axis that is coming that would be going through any one of these kind of dashed portions. So on the neutral axis we have point A, and we have our transverse force P that is pushing upward like this. Okay, so you see that this is rotated 90 degrees. This is now down, and we're looking at the profile along the length of the beam. If we take a slice, what we see is that we're going to expose, let's say, this section here, which could be right on, right going through A, or going right through A. And we get to choose what the external loads are from the wall on the structure. So we have R, which is going to be chosen to go downward to counteract P, and MR is going to be clockwise, which kind of makes sense to counteract the P times whatever the length of this beam might be. I haven't put much thought into these reaction forces, or reaction force and reaction moment, but I have an idea that I would like them to be positive, and I get to choose whatever I want for the external loads. Internally speaking, though, I've got to follow the convention. So the convention that we're using, based on Hibbler's book, is that V should be going downward when you cover up the right side, and that M should be counterclockwise when you cover up the right side. Now, let's sum the forces in the vertical direction, which would be in the z direction. And what we get is that we have minus v minus r is equal to 0. So v, the internal shear force, v has to be equal to minus r. We also know, and maybe I did this kind of quickly, that this r has to be equal to p. Okay, you see that? P is pushing upward, R would be from the wall down. So R is equal to P, and now we can say that V is equal to minus P. If we were to draw a similar diagram to what we just had here, and it's really identical, except now I'm saying, okay, this is downward, and instead of V, I've put minus P. Okay, that means that we're going to have a P acting upward, okay? And that P is in the minus Z direction, which this P was also in the minus Z direction, or this P, or this P. And so the internal shear force is in the same direction as the applied transverse force here, and it is the same magnitude. This is an important realization that you want to make when you start to see these types of problems. That if I have a transverse force being applied to a beam, I can, at any cross section along here, I can essentially just cut it and say, oh, it's the same direction and same magnitude as this P, which makes this diagram that I was talking about more straightforward and easy to draw than going through all this effort that we just did. Once you've kind of realized how we got to this simple drawing, okay, and so that's what we're doing here. Again, a little bit more detail and an extra drawing that you wouldn't necessarily need to do every time. But if I took a slice now, all right, so this is a slightly different perspective. It's going to the right. And this is a slice at location A. And this here is what we'll call the neutral axis, right? This was the longitudinal axis, and I might have been a little bit confusing about that in the few seconds ago in this video. But this is now what we'll call the neutral axis, and A is on that neutral axis, and these are the appropriate coordinates for the vertical direction. That's going to be Z downward, and for the y direction, which is to the left. Okay, so you can see this has been rotated such that A, was here, and now A, we're looking at it on the side here, and these are the coordinates that still align with what we said previously. That shear force, that internal shear force P, right? That was what V was, I can draw it upward as we see here, right? Because V would have been downward, but that would be minus P. So now I put a positive P and I can draw upward. And again, that lines up very nicely with what we have here on this diagram. If we think about the transverse shear stress on this face, we know that if you have, and you can go back and look at the notes for calculating out transverse shear stress for a beam, that if you're at the top or the bottom of the beam, so like y equals, or y prime, depending on however you want to draw it out, but y prime equals c, or y prime equals minus c. We know at the top or the bottom, the transverse shear stress is going to be 0. But at the neutral axis, we know that we're going to have the maximum shear stress. So we think about that a little bit, even as we're writing our formula for the transverse shear stress, which is V quit, or VQ over IT. And since it's on the neutral axis, and since we know it's maximum on the neutral axis, we really don't want to solve this problem in detail. We can go back to an expression that we derived for a cylindrical cross-section, or circular cross-section for a cylindrical beam. We can say that the maximum transverse shear stress is 4/3 times the average shear stress. If this were a rectangular cross-section, which it's not, then we could say that it's 3/2 times the average shear stress. What is the average shear stress? Well, the average shear stress will be the force P, or negative P because it's really V, divided by whatever this area is. So that's going to be pi c squared. So we put a 4/3 in front of it, and we say we have minus P, and it's going to be uh, over pi c squared. Okay? And this is the expression for tau x z. Notice, even if we sometimes I suggest not thinking too much about the signs, but until the end, and that can be a little bit dangerous. But if we know what the magnitude is, and we know that this P is acting in the minus z direction, then when we think, oh, okay, I need a tau xz, x is the x face, that's what's coming out of this, and z is down, down vertically, okay, positive, but P is in the opposite direction, so that's in the minus z. So I can kind of get that, okay, it's going to be minus P over the cross-sectional area times the appropriate factor, okay, 4/3. Oh, so all that just for the transverse shear stress. Okay, the next part, promise, goes much more quickly. Let's draw for our thinking of the structure as a rod with an applied torque, Tap. Let's just draw this cross section, and of course this cross section we might think of as being at a location A. And we also can think about the reaction force on this side, okay, on the back side, because I'm going to have that reaction force on this back side, and that's going to affect the internal, did I say force? I mean reaction torque, okay, the internal reaction torque that I'm going to have, or the internal torque that I'm going to have when I get to that slice. So the reaction torque here is TR, and you can see that that goes against Tap, and that same TR that I have here is, acting on this system here, but this is sliced. And I haven't had to follow a convention yet, but now it's probably a good idea to keep track of things with a convention. Remember, I draw the X face, and I have an X vector coming out, and so the torque that I'm thinking about, the internal torque, that one I'm going to say, okay, follows the right-hand rule with this x direction. So Ti will be drawn like this. When we're calculating out these shear stresses, or any type of stresses, it's a good idea to be using the internal force or internal torque for those calculations. After all, the stresses are internal representations of what's happening inside the material. Okay, so now I've got my internal torque, I've got my TR, and I've got a Tap. Well, let's relate the TI to TR to Tap. TR is equal to Tap, as we see here. And if we sum the moments, or the torques, in the x direction, and we get them equal to 0, we can say that we have a Ti, which is positive, and a TR, which is negative. So Ti is going to be equal to TR, which is equal to Tap. Okay, so we now know the internal torque. What is the stress? What does the stress look like on this face? Well, remember, it is going to be 0 at the center line, and it's going to be increasing until it gets to the outer surface, till it gets to rho equals c. So this stress, this gradient, it's going to be acting uh, in a direction that is circumferential, okay? So normal to the radial direction. So the radial direction would be from the center line to A, and then we have normal to it, like we see here with these different left arrows. And we see that okay, these stresses are acting in the z direction. Okay, you see that, right? This was z over here, and so the way we've sliced things, it's acting in the z direction. And which face is it? It's on the x face. So it's going to be a tau xz shear stress. And x is, well, coming out this way, so that's a positive, and it's positive in the z direction. So tau xz is going to be positive. A little more analytical calculation here. We have tau, generally speaking, for these shear stresses associated with twisting, is going to be torque times rho divided by j. And we can say that the tau xz at A is going to be the internal torque, Ti, times the distance from the center line, which we say is rho, but when we get out to the outer surface, it's just c, it's the radius of the structure, over j, the second moment of area. So that's going to be Tap times c over j. J is equal to pi over 2 times c to the fourth. And one way I remember j, at least when it comes to the second moment of area, and the polar one at that, okay, that there's an I that we sometimes use, and we use j for these types of circular cross sections that are under twisting. So I is pi over 4 c to the fourth, okay? And so I comes before j, so I is less than j. So I remember pi over 4 for the second moment of area for a rectangular cross section, and then if I need the polar moment of area for a circular cross section, the j, it comes later in the alphabet, so it's going to be pi over 2. It's larger than the I, so pi over 2 c to the fourth. We can now essentially just add these two to each other. Yeah, and I would be for a circular cross section. I guess I should say that, right? Not the pi over 4 to c to the fourth. That's for a circular cross section, not a square cross section. Square cross section, I would be bh cubed over 12. A rectangular cross section would be h cubed over 12. And if a is the side of the length, then it would be, for a square cross section, it'd be like it would be a to the fourth over 12. Anyway, just trying to make sure that I'm not spewing things that are incorrect. Okay, so tau xz at A, the total one, is going to be the tau max due to the transverse shear force, which is giving a transverse shear stress, as given by this quantity here, so minus 4p over 3 pi c squared. And then plus the contribution from tau xza from the internal torque, Ti, and twisting. So that's 2 times Tap over pi c cubed. That's the answer, and I hope this has been helpful in understanding how to treat combined loads on a shaft or beam.